Hi, so I'm Caleb Meredith. I will not be speaking French today, unlike our previous lovely sponsors, and I will try not to be speaking in typing judgments either, but we'll see. So I really like programming languages, and calling this a pro-reason talk is, my opinion on reason is a bit more nuanced, but I really like programming language design. It's something that interests me a lot. So I was thinking, okay, if I'm going to be giving a talk, I want to give a talk about programming language design, and it's like a very broad field. So I ended up deciding that I wanted to talk about a concept that I find to be the most important in programming language design, which is subtyping, which, as you can see by the slide, there's some fun academic papers with way more complicated language than what I will try to use, and why subtyping is important to me and my perspective of programming language design and how it impacts various languages. So yeah, let's get started. Let's have fun. My name is Caleb Meredith. I work at Facebook. I'm currently working at Oculus. In the past, I've worked on Flow, Apollo. I've worked on PostgreSQL, if you've heard of that. Yeah, so that's a bit about me. And let's jump right in. So this talk is about a bunch of programming languages, right? So this is a React conference, so most of us are probably JavaScript developers. But I get the idea that there are a fair number of people who have programmed in a different language or who are interested in another programming language, like maybe Reason. just a little guess. So yes, so let's ask a couple questions. So who here has written a line of JavaScript code? All right, I'm glad. I expected that. Who here has written a line of OCaml or Reason code? So that's a lot of people. Who here has written a line of C#? All right, well, I was expecting more hands for Reason OCaml. But I actually, if we look at the curve of what languages people use, it's interesting that we have a disproportionate number of people interested in OCaml and Reason. When we look at industry standard practices, everyone's using C# or everyone is using JavaScript. So I'm very happy I can talk about OCaml because OCaml is a nice little language with a lot of interesting ideas. So yeah, I'm happy I can talk about it. But the more in question is, why do I have a picture of a puppy and why do I have a picture of a palm tree on my slides? And why are they labeled as JavaScript and OCaml? Am I trying to identify JavaScript with puppies and trying to sneak into your brains that way? Now, let's change the labels to something a little more sensical. On the left we have animals, and on the right we have plants. Right? That's kind of obvious, right? So on animals we have dogs and cats, and for plants we have trees and bushes, and name your favorite plants. So when it comes to life on this planet, there are many ways we can categorize different forms of life. And I'm gonna completely ruin this biology speak here, but I guess there are two broad categories you could think of in macro level life. We have animals and we have plants, and you can divide them by multiple different categories. You can say, okay, green things are plants and things that are not green are animals. But that is not a great categorization because we have lizards, and lizards are green, and lizards are not plants. A better way of classifying macro-level organisms is, organisms that obtain their energy through photosynthesis and those that don't. So plants obtain their energy through photosynthesis. They, sit in the sun, soak it all up. And one of my biology teachers once said that the best superpower ever would to be able to have photosynthesis. I lived in Florida at the time, so I think he just wanted to spend all of his time on the beach, but okay. So we separate plants and animals by photosynthesis. And I claim that the best way to separate these lists of programming languages is not by object-oriented versus functional or static types versus dynamic types, but languages with subtyping and languages without subtyping, with a little asterisk, languages without explicit subtyping. So implicit subtyping is the thing I'm really talking about here. So yes, and before I define subtyping, I'm going to go through a couple of those other categories people normally like to use to classify their programming languages, such as dynamically typed versus statically typed. So if we look at these languages, you might say, well, let's move Java and Objective-C over to the other side because JavaScript and Python and Ruby are dynamically typed. And yeah, you could use that and describe languages this way. But I find that description a little messy because from a language design perspective, All of these languages have dynamic aspects, and even JavaScript and Ruby have static aspects. So if we look at Java, we have like instance of. If you look at Objective-C, all messages are dispatched dynamically. If you look at OCaml, you have ObjMagic. If you look at Haskell, you have a dynamic type, right? So every language on these slides, I was able to find a way to interact with types at runtime in a dynamic way. So it's like, okay, well, then the difference is dynamic as a default versus static as a default. And you could say, okay, so Java has a static type system, JavaScript doesn't. That makes Java a statically typed language, but JavaScript a dynamically typed language. And to that I say, well, JavaScript does have some static rules. If you look at the JavaScript specification, there are like two sections. There are the runtime semantics for the JavaScript specification, but there are also the static semantics. And what the static semantics don't let you do things like write const x equals 1, then const x equals 2. It'll throw an error. So you can't define x twice. So while it's not static typing, while it's not in the same way that OCaml might have static typing, JavaScript and Ruby and these other languages still do have static rules. So it's like, okay, JavaScript has static rules. Java lets you manipulate objects dynamically. But if we look at the runtimes, JavaScript has a dynamic runtime, and you don't know type information at runtime. Well, if we look at the JavaScript runtime and we look at the OCaml runtime, they're very similar. So JavaScript uses this idea of tagged pointers, and that is how you can store a Boolean and an integer in the same field, or a pointer to an object. OCaml does the same thing, because it's good for garbage collection. So if we go down into the runtimes even, the distinction is a little murky. So dynamic versus statically typed is a distinction we can use, but it's a little murky, and it's a little less clean than using subtyping versus no subtyping. So another thing people like to use is, okay, these are my object-oriented programming languages, and these are my functional programming languages. And for functional programmers, this is like, let's go to the best functional programming languages where I can have a lot of fun writing my maps and my filters and my hierarchical functions. Well, all these languages have lambdas. So that means you can recreate any form of lambda calculus. You can have all your hierarchical functions in any of these languages. It may be the syntax might be a little more difficult in one versus the other, but you can recreate these basic concepts in any of them because you have this, the basic three, the three things you need for lambda calculus, which the most important one is lambda expressions. And OCaml also has classes. So while we have all the languages on the left having object-oriented patterns and class-based inheritance, on the right, OCaml has an object system and has classes. In fact, OCaml, which stands for Objective Camel, it has object in the name. And throughout this talk, I'm going to be saying OCaml, and for those of you who like reason more, you can substitute the word OCaml for reason in your head, and it's basically the same thing. Yes, and Haskell and Rust don't have traditional object-oriented classes. Haskell has a class keyword and has type classes, but they aren't traditional classes. They're different in that they don't use subtyping, which is what this talk is about. Yes, so type classes allow for some of the behavior. But as we can look at this list, we can start to see the difference between languages with subtyping and languages without subtyping. Notably, all the languages with subtyping have classes and have object-oriented patterns. So you can kind of think in your mind this difference between implicit subtyping and no implicit subtyping is the existence of object-oriented patterns. And now, why is this? We've came a long way, and now we should ask the question, all right, well, what is subtyping? And so I know you're not supposed to do this, but I'm going to read from my slides real quick. So subtyping is a relationship between two types in a static type system or in a dynamic type system, where A is a subtype of B if any function that can safely operate on A can also can safely operate on an instance of B can also safely operate on an instance of A. All right, those are a lot of words. They probably went over most of your heads. So the way I like to describe this is as two circles, right? So B is this really big circle that includes a lot of values, right? It includes the number 1, includes the number 2, includes the number 3. So if you can go back to kindergarten or elementary school when you learned about Venn diagrams and sets, so B is this really big circle that contains a lot of numbers and a lot of values in that circle. And A is a smaller circle that is completely inside of B. So if B has the numbers 1, 2, 3, 4, 5, 6, etc., and A only has numbers 1, 2, and 3, because 1, 2, and 3 are in both A and B, and A has no other elements, it is a subset of B. It is a circle, a small circle, inside the larger circle of B. So A is a subset of B. A is also a subtype of B. So that's like the basic explanation. Big circle, little circle. If the little circle is inside the big circle, then we can say the little circle is a subtype of that. So how do we translate that into code? And I have a couple of examples of flow types or TypeScript types, or pick your JavaScript type system flavor of choice, and how they relate to each other from a subtyping perspective. So if we have a class of animal, for instance, and we have a class of cat, and cat extends animal, then the class cat is a subtype of the class animal. Why? Because any function you write that can operate on an animal can also operate on a class, because cat is a subclass of animal, and so it is also a subtype of animal. So we also have a union of the numbers 1, 2, and 3, and that union is a subtype of the much larger type of number, right? So 1, 2, and 3, all of those 3 numbers are included in the much larger circle of all numbers you can express in JavaScript. Similarly, if you have Boolean, which is true and false, that is a subtype of the much larger circle of the union of strings and Booleans. Okay. So, and then finally, we have an object type, which says, okay, an object type with the property ID and name is a subtype of an object with just the property name. And this is to demonstrate that the type that you write in Flow or TypeScript does not have to be bigger for one type to be a subtype of another, right? So the type with just the property name, you write it, and it's smaller. You write colons, then you write name, colon, and so in the number of characters you write, it is smaller, but it includes more values. Why? Because you could have ID, you could not have ID. ID could be a Boolean, ID could be anything. So it's a bigger circle in the sense that more values can be expressed by the type of mustache braces, name, colon, string. Okay. So subtyping is very popular. As we saw on the list, basically all the money in the world goes to languages with subtyping. And why is that, right? So subtyping allows us to express abstractions in object-oriented designs. And a lot of us really like object-oriented programming. So, you write your class animal, and it has a method of dance. Then you can have your class cat and your class dog, and they can extend animal. They can have completely different memory structures, and you can put them all in a list. You can say, my new cat, my new dog, and have a list of all my animals together, and then call dance on them. And then that's great. That's subtyping, right? Because the function that calls the method dance operates on any instance of animal. So anything that is a subtype of animal, calling the method dance will also work on that. Okay. So, but despite having, but even though we have this, list of animals, as we can see on the screen, with cats and dogs, they have completely different memory layouts, right? So, cat has a property of meows, dog has a property of barks, right? So completely different memory layouts, but they're all mixed in this one array, and you can call a dance on all of them. Okay. And as a programmer, you only think about the animal contract. It's just an object. But subtyping adds overhead, right? Because when you call animal.dance, there are a couple of different implementations, right? So you could have, if we think about how JavaScript objects work, and we think about the prototype chain, animal.prototype.dance, so that could be the method you call, or the function you call. It could be cat.prototype.dance. It could be dog.prototype.dance. And there's no way for us to know when we call the method dance statically exactly which function is going to be called at runtime. So that means the runtime has to do a little bit of work seeing, okay, is this a cat? Is this a dog? Is this an animal? Which function do I route to, right? And so the JavaScript specification adds a little bit of text explaining how this works, right? So this is just basically the prototype chain lookup in the JavaScript specification, right? So in order for JavaScript to resolve which function to actually call, when you call dance at the very bottom of the screen here, JavaScript has to look first at the own properties of your object, then it's like, nope, not here. So it has to go to the prototype and look it up in the prototype, and if it finds it, it calls it. If it doesn't, it has to go to the next step, right? So the thing that subtyping does is, while it allows you to write code that operates on a bunch of different values, it adds overhead at runtime, a small bit of overhead, right? Not a lot at all, but a tiny bit of overhead that requires some dynamic method resolution to actually figure out which code it's going to run next. Instead of saying, okay, this is I'm going to dance as a cat. It's like, okay, am I dancing as a cat? Am I dancing as a dog? Am I dancing as a generic animal? We don't know until runtime, and we have to look it up. And if you're sitting there thinking, haha, JavaScript, this is the JVM. So any language you might write on the JVM does a very similar process where it looks up in a class's own properties, doesn't find anything, goes to the subclass, doesn't find anything, goes to the superclass. And it just keeps doing that until it looks something up, right? So in order to write better code as a programmer, we accept this implicit cost, which is kind of sad. We would like to write programs that are super efficient while being able to keep our abstractions. So that's subtyping. Again, subtyping adds overhead because you need to be able to run certain operations on the same values. So that means those values need to have a memory representation, and you need to add some runtime overhead to dynamically dispatch whatever code you're going to run on these very different values. So it just adds a little bit of overhead. And that's sad. That must be the cost of programming in a higher level programming language, right? Well, wrong. We don't need this overhead, right? So the title of my talk is Subtyping is Overrated. That's because if we look at this list, we can see that basically all the money that goes to programming in the world goes to the list of languages with subtyping, goes to the list of languages with object-oriented patterns. So just because they have subtyping does not mean they're bad. Again, this overhead is very, very small, but I think we should ask ourselves, okay, well, is there a way to take the abstractions we like to build? Is there a way to take React? Is there a way to take these GraphQL, these abstractions we love to work with, and make them efficient by default, and not accept this extra little runtime overhead that's required to look up a method on the prototype chain? And the answer is yes, because some languages have done it. And those languages are OCaml / Reason, Haskell, and Rust. And while they do have a bit of explicit subtyping, when you want to enter into dynamic land and have something like dynamic method dispatch, you have to explicitly say, okay, let's take my OCaml object and explicitly cast it to its subtype, okay, or to its supertype. So subtyping is not abstraction. So here I have an image of algebraic data structures in OCaml, and here you have, okay, like type of animal, and it has two variants, cat or dog. And then we have a function with a match branch with cat or dog, and we finally call it dance on that. Okay, so what's the advantage here? The advantage here is we don't have to have any runtime overhead in order to figure out which dance function we're going to call. Instead, we know exactly the code we're going to run when we say call dance. We know the exact function, and then in order to branch, in order to get our polymorphism, then it's just a quick switch, a quick match switch in our compiler, which is much faster than dynamically resolving which method of dance in an object-oriented system. Right? So there is no cat type, there is no dog type, right? There is just an animal type. So there's no complicated subtyping relationships. In OCaml, there is just one animal type, and this makes things like inference easier, type inference. This makes a lot of things simpler from a programmer's perspective, and it makes the runtime simpler. It removes a bit of that overhead. So see, you can obtain abstraction without having to use subtyping. And in Haskell, there's this similar method, which is called type classes, where you can do this with kind of like an open end of variance. So in OCaml, you kind of have like a closed list. You have cat and dog and nothing else. There are no other animals in the entire universe. With Haskell, you can have a type class animal, and that is open. So you can create a new data structure for cats, you can create a new data structure for dogs, and implement animal on that data class. Yes, so Haskell uses the similar method, but with the difference that you can't mix cats and dogs in the same list. So this is interesting. So when you have a type class in Haskell, this type class is then a constraint on types. And if you try to make a list that mixes cat and dogs and say, this is a list of animals, Haskell will complain, because that means at runtime, when you try to call dance on that list, Haskell will not know whether we are dancing as a cat or whether we are dancing as a dog. Instead, you must explicitly say, okay, this is a list of cats, and Haskell will know, all right, we are dancing as cats, or this is a list of dogs, and Haskell's like, okay, we're dancing on dogs. And you can switch between the OCaml style of type variants, which also are included in Haskell, and these type classes, depending on what situation you're in, to regain these abstractions you're losing. And Rust has another fun concept called box traits, which takes this idea And when you box a trait, this is a form of explicit subtyping. When you box a trait, it adds a little vtable to it at runtime. So while statically, you may be able to statically resolve, okay, I'm dancing as an animal, or I'm dancing as a cat, or I'm dancing as a dog. If you want to add a bit of dynamism, then in Rust, you could use a boxed trait and put that around your type class. And at runtime, Rust will add in a little vtable, and when you call dance, it'll be like, okay, where am I going for my dancing as cat or dancing as dog? So it'll add the extra little bit of information as to what specific function to call when you box up the trait. So like there are multiple different methods to regain these abstractions that we like from object-oriented programming in a language without subtyping and in a language without these extra little overheads. And again, I want to make clear that the overhead from subtyping is not very large, but I feel like we should be able to demand more from our programming languages. That we should demand not just easy to use, fun to use, and nice syntax, good editor support, but also that the abstractions we write work well from a performance aspect, that don't have a lot of overhead by default, so that we're working at a place where we're writing beautiful code, but at the same time this code is efficient by default, and instead of having a bunch of overheads by default. So yeah. That's the bits I wanted to talk about, subtyping about. Of course, the programming language design is a deep and complicated field, so there is a large deep end of much more things we could talk about, from explicit subtyping in OCaml and Rust, to OCaml's object system, to polymorphism in different languages, to how Elm does row polymorphism and records. So yes, there's much more deep end if you would like to explore these topics more and would like to learn more about programming language design. So thank you. That has been my talk about subtyping.